of the due dates, and then we'll go ahead from there. So as far as the due dates go, the language of hypothesis testing, that was the section we finished last time. That homework is due tonight, so please make sure you do that homework. Additionally, the homework corresponding to the section we will be talking about today, that is due on Friday. So make sure you keep those two due dates in mind. Besides for that, that's really all there is for this class in terms of this week. So nothing really due over the weekend. So next thing that'll be due in this class will probably be Tuesday or Wednesday. So once you get those done, you have a nice little break. So does anyone have any questions for me before we get started? If not, then, all right, so let's go ahead and move on to the new section. New section on hypothesis testing for population proportion. Now, for this section and the next section, so we talked about the language of hypothesis testing in the previous section, about what it means to have a null and an alternative hypothesis. It means to reject or not reject the null hypothesis, and some of the consequences for doing so, and some of the lingo ultimately that's used in this whole process. And so since we established some of the initial terminology, we can go ahead and apply it to one of these parameters. So you might notice in the last, or 2 chapters ago, we talked about specifying things for mean and proportion. In the previous chapter, we specified things for mean and proportion. In this chapter, we're going to, again, specify things for mean and proportion. And so we start off with the proportion here. So we're using hypothesis testing for the population proportion, but we need to clear up some generalities first, some things that apply to just hypothesis testing in general. And one thing we need to learn about is something called a p-value. And a p-value is a probability value. So a p-value is a probability that a sample will result in a statistic such as the one obtained if the null hypothesis is true. Now, this is more technical than anything, and I like to think about it more as it corresponds to the probability of a z-score. And I'm going to highlight down here what it ultimately in this section pertains to. So it does end up being, if we were to use the z-score table that we used, I believe, for the second exam, then we would have to use that, and we would have to find this value here. Now, as we will see, we don't have to worry about that as much, and I'll show you all momentarily why we don't. But the p-value is a certain probability value. And what it's asking for, ultimately, we're finding this probability value, and we're going to determine, is this probability greater than or less than a certain level of significance? We talked about the level of significance in the last section, and it comes up more so here, but we're getting a new probability to compare to another probability, and depending on which one is greater than the other, that tells us whether we should reject the null hypothesis or not. So using a p-value is known as the p-value approach. You might see that in the homework a few times. That's the method we will use. There's 2 other methods, and we're going to use what's called the p-value approach. And to specify it here, how it works, if the p-value is smaller than the value in the null hypothesis, which I'll explain momentarily, reject the null hypothesis. So not larger, smaller. We reject the null hypothesis based off of if this probability is smaller than this. So let's go ahead and look at, so I do mention the formula for a test statistic, and it is a little bit algebraically, I guess, time consuming. Luckily, the calculator will give us this value automatically. As we'll see, you might be able to see later on in the notes if you have the notes printed out. But more so, we're going to talk about the step-by-step process on how to apply the testing hypothesis towards a population proportion. And so to even use a hypothesis test on a proportion, three things have to be true. And we've seen these before. So these three conditions have to be true. Or in other words, these must be true. Now, I'm going to say that the first one and the third one, as far as the scope of this class goes, we can just always assume that those two are going to be true. So if you get any question that asks you to verify this, you can always assume that the first one and the third one are going to be true. They're kind of tedious. And so that leaves for you to determine that the middle one is correct, because that one you can actually figure out, and the computation isn't too bad. So you would end up testing this one. And we'll see that in these example problems coming up here. But once you verify that these three conditions are in fact true, that allows you to use hypothesis testing. Once those three are satisfied, you can use hypothesis testing, which means you go through the steps for hypothesis testing. You determine the null and alternative hypotheses, like we did in the previous section. Determine if the hypotheses are two-tailed, left-tailed, or right-tailed. We also talked about that in the last section. So that's some of the terminology that helps us out with this process. It does say select a level of significance, alpha. Normally in this section, generally they will give us an alpha, a value for alpha, which is a probability to ultimately consider and compare. So again, remember we defined this in the last section. Alpha corresponds to the probability of making a type 1 error. We defined this at the end of the last section. So once you have how your hypotheses are, how their characteristics work in terms of the tails, you have your alpha, which is your probability of making a type 1 error. And then you're going to compute this thing called the p-value using your calculator, which we'll talk about here momentarily. If the p-value is less than alpha, so this is the important thing here. If the p-value is less than alpha, we will be rejecting the null hypothesis. So in the last section, we didn't talk about how to reject the null hypothesis. We talked about what conclusions do you make if you reject it, or if you do not reject the null hypothesis. Here we talk about when do you reject the null hypothesis. And then we can state the conclusion. So this step-by-step process, I mean, the good news is that the homework does elicit the step-by-step process as well. So it will talk you through these steps. So besides for that, I suppose let's look at an example here. So example 1 here says, test the hypothesis using the p-value approach, and they give us a ton of values. And so let's try to remember what some of this terminology refers to. H0 is the null. H1 is the alternative. The null hypothesis is what's assumed to be true, as we talked about last time in class. The alternative is some, well, alternate idea. So one says that one claims that the probability would be 81%, and then the alternative hypothesis says maybe the null hypothesis is not correct. Maybe the percentage is some other number. It also tells you the sample size. Maybe they went out and interviewed 500 people, and maybe 390 of them agreed to some characteristic. Since we're talking about proportions, then this normally these are categorical outputs, yes or no's. And they also, as I mentioned, give us a level of significance. They give us a level of significance. So they gave us a lot of information here, and they told us the probability they feel comfortable with for making a type 1 error. So they're pretty much saying we want to be 99% sure that we do not make a type 1 error. And the reason I get 99 is because we're looking straight at its complement. 0.01 corresponds to 1%. Complement of 1% is 99%. So they want to be 99% sure that they do not make a type 1 error. And then part A. So part A is this verification process. This is, can we actually use hypothesis testing? And out of the 3 conditions we talked about, I told you don't worry about 2 of them, and you'll only have to check 1. In part A, this is us checking that 1 condition. Now we know what n is. N is 500. Now what is P0? That's the question here. What is P0? P0, note that P0 is the assumed value of the population proportion. Yeah, that's going to be the 0.81 thing right here. It's the value that is assumed to be true. This is P0. So that's always going to be true. So there's quite a lot of values floating around here. So basically we know what n is. N is 500 times P0, which we just said to be 0.81. 1 minus 0.81. We ask ourselves, is this greater than or equal to 10? So very quick computation we can check. So 500 times 0.81 times 1 minus 0.81. Yes, it's definitely greater than 10. So we just verified that. That's all we did. We just verified, hey, now we can use hypothesis testing. So this is, in fact, greater than or equal to 10. So we verified this condition. So hypothesis testing can be used. If this condition failed, then what this tells you is that you didn't sample enough people in your study. You need to go out and find more people to study. But here it seems like 500 is plenty enough. Now they want us to determine p hat. So we've actually seen p hat before. In fact, we found this many sections ago. P hat is just x divided by n. It's just the number of people that have a characteristic divided by the total number of people surveyed. For example, they might have went out and interviewed 500 people and found that 390 of them were females or something, just a very binary output. And they want to know the proportion of this, which is simply just 390 divided by 500. Is it 0.78? Yeah. 0.78, okay, cool. 0.78. All right. So from here, now we're going to, this is where the calculator is going to be helpful. Determine the test statistic Z0 and the p-value. Now the test statistic, I did give a formula for it all the way up here. So just to show you all where it came from and how it helps us. So if we were to do this by hand, which we're not, but I just want to explain the motivation, the test statistic gives us a z-score, and that z-score would be used to help us find the area. So if we did this by hand, you'd have to find the z-score using this not very nice looking formula, and then you'd have to go to the table in the back of the book. You'd have to probably complement this. So this might sound familiar. Again, you don't have to do this process, but if we did this by hand, you'd have to take that z-score that you find, the test statistic, you'd have to go to this table with the z-score and find the area, but then you'd have to subtract that area from 1 because the inequality symbol is not in the correct way. So instead, the way we do this in the calculator, and I'll put this on the screen here as well. So we have a new calculator tutorial, finding the test statistic and the p-value for the population proportion. So you click on stat here, scroll over to test, and you go down to, it's labeled 5, it's the 5th one. It's one proportion Z test over here, so it's the 5th one. When you press enter on that, you should get the screen here, and it should say one proportion Z test at the top. Now notice it's asking for, well, really 4 things here. It wants P0, which we found. P0 was the 0.81. It wants X, okay, that was 390. They gave us that. They want N, which is 500. But it's all they want is P0, X, and N. They don't really want anything else. And they also want to know how your hypotheses are tailed. Is it a 2-tail, a 1-tail, a 1-tail to the left or to the right? And this is always based off of the alternative hypothesis. The alternative hypothesis tells us that we have a not equal sign. Well, guess which one of these we select? The not equal one is already selected. So we follow that in reference to whatever the alternative hypothesis tells us. So you should have exactly what's on my screen. Once you have that, you can calculate. Again, that's the screen that corresponds to this part of my notes. So calculate. And notice they give us a z value, the negative 1.7, all that stuff, and a p-value, the 0.08, all of that stuff. And then they verify the fact that we have a 2-tail, and they, again, show us the, they show us the point estimate, really, the sample proportion, the 0.78 and 500. It actually gives us a good bit of information here. So the calculator tells us that the test statistic is negative 1.7, we'll call it 1. And that the p-value is 0.087. Actually, I'll do 3 decimal places. However many they specify in the homework, and just go with what they have. So I'll do 3 decimal places. So from here, so that's the test statistic and the p-value. Now really, we don't need the test statistic because that would help us find the p-value, but the p-value is given to us automatically by the calculator. But the homework asks for it, so you can go ahead and provide it in the same process you would to find the p-value. And then we state the conclusion of the hypothesis test. Now, the way we do this, now that we have the p-value, this is the main thing we need, the p-value. So this conclusion of the hypothesis test, it comes down to comparing the p-value to alpha. So since the p-value is 0.087, alpha is 0.01. So since the p-value is greater than alpha, we do not reject the null hypothesis. We do not reject the null hypothesis. That's what this tells us. If the inequality symbol was flipped, we would reject the null hypothesis, which means we would conclude with the alternative hypothesis. But basically, we did not find enough evidence to overturn our assumption. Now, it doesn't mean that the null hypothesis is conclusive. It just means that we didn't find enough evidence to overturn it. It's like with the court proceeding, the analogy I mentioned last time. And so this is the general process. Mainly, it's the calculator is very useful here. It's just up to you to remember how to compare some of these bits of information together. Does anyone have any questions before we look at the next example? If not, let's move on to a similar problem, but a word problem now. So a study in 1994 found that 48% of parents with children pretty much in grade school were satisfied with the quality of education their child received. A more recent study found that 544 of 800 parents were satisfied with the quality of education their children receive. And so it was 48% before, and now it's 544 out of 800. And then what this asks us, are parents more satisfied about their children's education now than back in 1994? And then they tell us use the 0.05 level of significance. So again, they gave us alpha as well. And then part A, so this is loosely based off of how the homework presents this information. Verify the 3 conditions required for testing the hypothesis. Now, again, so the 3 conditions, this comes back to the sample is obtained by simple random sampling and the sampled values are independent of each other. Really, however you end up wording it on there, however it asks you, you will verify those 2. So for the 3 conditions, you need to pick whatever choices correspond to saying there is a simple random sampling and the sampled values are independent of each other. Simple random sampling, sampled values are independent of each other. So As I mentioned, you're just going to assume that these two are true. These are kind of a pain to really talk about thoroughly. Simple random sample, check. The second one is samples are independent. And then the third one is the one we need to test. This is asking, does n p0, 1 minus p0, is that quantity greater than or equal to 10? So I guess not does, but is. That's a better way. So is, rather. So that implies that we need to figure out what n is and what p is. Now it looks like n, so remember n is the sample size. N seems to be 800. That's the total number of people interviewed. P0 is the quantity that's used and what will end up being the null and alternative hypotheses. It's the assumed proportion. It seems like it's assumed that the proportion is 48%, or in other words, 0.48. That's the assumed proportion. They told us it was 48%. So since we know these two values, we can quickly figure out, does this actually hold? Can we use hypothesis testing in this situation? So we can quickly plug this into the calculator. And we definitely get a number that's greater than 10. So this is true. So the third condition is true. Now from here, we can go ahead and determine now, so just like we did in the previous section, what are the null and alternative hypotheses? And so remember, the null hypothesis is H0. What we did in the previous section, we needed to determine what the symbolism was, and we needed to figure out what ultimately what the P0 value is, the assumed proportion, to start off with the null hypothesis. So here we see that the assumed proportion, so proportion implies we're using the variable p, and this claims that p is equal to 0.48. So it's assuming that the proportion is 0.48 or 48%. And the way they word it on your homework, they use the word versus as a way to contrast these two, which makes sense. Only one or the other is going to be correct here. And this is versus the alternative hypothesis. Now, the alternative hypothesis takes on the same form, but we just need to figure out what inequality it takes on. So they're asking about, are parents more satisfied? So they're asking, is this proportion going to be higher now? So are more parents satisfied? Which means we would be using a greater than sign. And so that's the null and alternative hypotheses. And once we have that, we can go ahead and go straight to the calculator. Because this also gives us an idea of what the tail is like. So they want us to find the test statistic and the p-value. We can again go to stat, move over to tests, go down to 5, which is 1 proportion z-test. P0 here is the assumed proportion. So 0.48. X here were the number of people who shared a certain characteristic. That's 544. That's 544 of the, 544 of the 800 people in total. And as far as the proportion tail characteristic, again, the alternative hypothesis always tells us which inequality to use. We use a greater than symbol. So a greater than symbol. Once you have all of these four values, or these three values in that one appropriate condition, we get for the test statistic 11.32. And for the p-value, we actually get 0. Now, e to the negative 30, that's a decimal place, followed by not 1, not 2, not 15, but 30 zeros. So that's a very, very, very small number, e to the negative 30. That is 0. That'd be 0.000, a whole bunch more zeros, in fact, 30 zeros, and then 519, so on and so forth. So that would round in any situation to 0. So we need to determine the conclusion for the hypothesis test. And this again comes down to comparing the p-value and the alpha, the level of significance value, which they gave us in this problem as 0.05. 0.05. So now we get that the p-value, since the p-value is less than alpha, we reject the null hypothesis. That's right. We reject the null hypothesis. I don't know why I'm writing this for p-values at. My fault. This is where the p-value goes. I need to write this down below. Since this is less than 0.05, so let's try that again. P-value here is less than alpha. We reject the null hypothesis. Really, using the language of hypothesis testing, we can conclude the alternative hypothesis. So if you don't reject the null hypothesis, it doesn't mean that the null hypothesis is true. It just means we didn't have enough evidence to reject it. But if we can reject the null hypothesis, there's only one option left. That's pretty much how that ties into the language that we use in the previous section. So what this is saying is that parents are, in fact, more satisfied with their children's education now than in 1994. Because that is the alternative hypothesis. Does anyone have any questions before we look at another example? I think this should be pretty straightforward stuff so far. The calculator gives us a lot of versatility here. So actually, example 3 came up with this one last night. So I hear from colleagues all the time that some teachers tell their students 80% of students will make the same grade or lower from their midterm grade to their final. And this is normally when the drop date comes up. Some teachers tell their students this. And so I hear this in the hallway, and I thought, let me test it out with some, I've taught a bunch of 105 classes. Let me take about 64 students and try to figure out how often it happens that someone gets either if someone gets the same grade or lower on their final, or if they actually raise their grade up. Now, it's definitely a lot more rare. And so I counted the frequency of how many times this happened. 50 students ended up with the same grade or lower from the midterm to the final. Had about 14 students got a better grade by, working really hard. So so this says verify the 3 conditions. Again, we're going to assume that 2 of these are already right. Let's just assume that I chose these as a simple random sample. And all the samples are independent. And so the only one we need to check is whether n times p0, 1 minus p0, if that is in fact greater than or equal to 10 or not. Now, the reason I had to pick 64 was because I worked this problem backwards, because I knew what p0 was, and it told me that I had to pick an n value at least at 62. Or something like that, 61 or 62. We'll see it here in a second. And so I chose 64. So from here, 64 students, that's the total number of people that I considered in the study. P0 is what's the proportion that's assumed to be true. That's 80%. Times 1 minus 80%, or 0.8. (64) times 0.8 times 1 minus 0.8. And we do, in fact, just get above the threshold. Pretty sure 62 would be the smallest sample size you could do before this would not be valid. Maybe it's 63, I can't remember. In any case, 3 conditions are valid, which means I sampled enough people in order to use hypothesis testing. Now from here, it's asking, what are the null and alternative hypotheses? Start off with the null hypothesis. Well, we're talking about proportion. So that's P. And it's assumed that the proportion is equal to 0.8 or 80%. Now the alternative hypothesis, well, basically all I'm doing here is checking whether the 80% is true or not. So really the inequality symbol is not equal to. I'm trying to see, is 80% right, or is it some other percentage?
I have a question.
Yes.
It says, I guess I'm just confused because it says in the example, we'll make the same grade or lower, so you would use like less than or equal to?
So that's just the criteria for counting the frequency. That isn't, so it's basically where is the inequality derived from? And that is a good point of consideration. But it's ultimately, what is your alternative hypothesis? And so my alternative hypothesis would be is 80% the true percentage, or is it some other proportion? Yeah, so that one is, yeah, I didn't think about that when making this problem, but I do see where you're coming from. It still is not equal to,
Okay.
but yeah, those inequality symbols in the table just help us count. Now, from here, let's go ahead and find the test statistic and the p-value. Now the question is, what do we put into the calculator? Go over to test, go back down to 5. Now the assumed proportion is 0.8. Now the question is, what's x and n?
What is it, 7?
You said 7? Where'd you get 7 from?
I decided to take this test with 64 students from several 105 classes.
From several Math 105 classes?
7, and then 7.
Several?
That's where I got it from, but I don't think it's right.
I mean, I think you're confusing 7 with several.
Those don't coincide.
So not that.
Never mind.
Let's try another number. What's x?
You have 2 numbers. You have 50 and 14.
So which one is it? It'll be 50.
How do you decide?
Because the reason why it's 50 and not 14 is, what is the 80% referring to? Yeah, the 80% is referring to the students that will make the same grade or lower. Now, the top inequality is the same grade or lower. That's why I chose 50 instead of 14. And then that's out of 64 people. So that choice does matter here. And we see from the alternative hypothesis that we use the not equal symbol. That tells us that we have a two-tailed test. As long as you have those 3 values and the not equal sign selected, we get a p-value. Well, let's start off with the test statistic here. The test statistic is negative 0.375. The p-value is 0.70, let's just call it 8. And then they want us to determine the conclusion for this hypothesis test. You might look at the problem and think, where's alpha? It didn't give us a value for alpha. And I claim we don't need alpha. So we don't need alpha here because our p-value is very large. Normally alpha is, well, it's a level of significance. It's the error, or it's the probability of committing an error. And so normally that's, at the largest, it's 5%. If you have a substantially large p-value, so this would correspond to 70.8%, that's going to be much larger than any value of alpha that we would select. So there is a problem like this in your homework where they don't give you the alpha, but you have to conclude that although we're not given alpha, the p-value is large enough really. By large enough, really anything greater than 0.1 would be definitely large enough. The p-value is large enough to I can't remember exactly the terminology they use. Ultimately, I want to say that we do not reject the null hypothesis because the p-value is large enough to where it would be larger than any practical choice of alpha. To conclude that we do not reject the null hypothesis. Or in other words, the p-value will be greater than alpha for any practical choice of alpha.
So anytime the p-value is larger than 0.1, don't reject.
Yes, so I think that's fair to say. If you because normally you want alpha to be a very tiny number, because that's the probability of committing a type 1 error. You don't want, the sound of that, you don't want a high probability of committing an error. You want a very small probability of committing an error. So normally alpha is chosen to be up as high as 5% in practice. Now, I give a little bit of leadway there as well. I bump it up from 5% to, let's just say, 10%. Now that's in practice, maybe there's not 10%, but my math lab, who knows? Anything over 10% for a p-value is definitely going to be strong enough to be larger than any reasonable choice of alpha. So although they do not give us an alpha, our probability is large enough so that way we know it's going to be larger than any choice of alpha that we may find. And so there is a homework question like this, and that you ought to see where the thought process comes from. If the p-value here was 0.025, and they didn't give you an alpha, you couldn't make any sort of conclusion, because you might have a level of significance that's 1% or 5, and those would give you different outcomes. But a p-value of almost 71%, that's much larger and will always be larger than any choice of alpha, any reasonable choice of alpha that you choose. So does anyone have any questions pertaining to this? Anyone? Well, that's all I have for today. So cutting class early. So you all get out of here.